Now we're moving on to what I consider the last piece of core OpenMP up to OpenMP 3.0. So after this section, you'll be able, you will have command of the SMP shared memory core of traditional OpenMP. And it is dealing with the data environment. That's like the last piece we haven't covered. After this, you're ready to just rip into OpenMP. All right, data environment. So remember, in OpenMP, when you have a variable is a name that attaches to a region of memory where you can store and load values. OpenMP is a shared memory programming model. So most of the time, if you define the variables prior to the OpenMP construct, they are shared. All threads can see them. If you do nothing, that's pretty much what you got. All right? But it gets a little more complicated. Global variables are shared among threads. So let's say I have Fortran common blocks. See, Fortran programmers, I don't completely ignore you. Or Fortran module variables. Or I have variables that are save variables. They're all shared. Okay, what about C? Okay, if I have file scope variables, or a variable that I declare as static, those are shared. So even if inside some function deeply buried inside of a thread and I have a static statement, that's going into a space that's shared to all the threads. And if I start calling malloc, that's a shared space. Okay? This is where, as an operating system person explained to me, malloc is going into the heap section or whatever the shared memory region of a process is organized as in a particular system, and therefore everyone can see it. So these are the things that become shared. But not everything is shared. Anything that goes on the thread's stack. So the automatic variables declared inside of a thread's, inside the structured block from which I created a thread. They're private. And the word we use is private. It's private to a thread. Only that thread can see it. I want to make sure that you really understand the default rules. And this is an official head nod slide when we get to the end of it. So look at it carefully. I have a piece of code. I declare an array called A. Then I have my main. Then I have an index of size 10. Now I have a pragma OMP parallel region. And this pragma OMP parallel region, the structured block, has a single statement. That single statement calls a function called work. Inside that function work, okay, I'm going to pick up the file scope variable for A. I'm going to then take in a command line argument for index. And I'm going to declare an automatic array temp, and then have a static variable int. That's count. All right? So what I want you to do is stare at this code and make sure you see why, prior to the parallel region, I got A, index, and count, and they are shared between all the threads. But inside each thread, they have their own copy of temp. All right? And then when we're done, we still have the values of A, index, and count that are visible, but temp goes out of scope and goes away. All right? Head nod? Head nod?
In this example, if you allocated temp dynamically, would it be shared or private?
If I allocated temp dynamically, would it be shared or private? That is a wonderful question. It really is. If I used a malloc statement to dynamically allocate that array temp, it would be shared and eligible to a race condition.
Is there any way to make it private?
Yes, and we're going to talk about that. Okay? Yes?
So you said when you malloc memory inside like this work function, it's all shared, right?
The malloc goes to a shared memory region of the process and therefore is visible to all threads.
So the first thread that hits that malloc statement, you actually allocate the memory.
If you have multiple threads mallocing and you do not have a race 3 malloc, all hell breaks loose. Okay? These are not things I would do in a program. All right? Let's just be clear. The next point, now that you understand the default rules, is how do we change the sharing attributes? So we have three clauses that I want to make sure you understand deeply, so I'll go through them very carefully. One is called shared, and it takes a comma-separated list of variables. And that basically says that, and I put these clauses on an OpenMP construct, a parallel construct, or one of the work-share constructs. And what that says is that these constructs, these variables, are shared inside this construct, which, of course, is the default behavior anyway, right? I mean, that's what you get, shared, right? Private says, here's a list, so it's a clause on a work-share construct or a parallel construct. And private says, here's this list of variables, create a copy of that variable for each thread with that name, but don't initialize it. That's what private says. So for example, in our Pi program this morning, remember I had to create a parallel region, then double X, then my loop. Okay, I could have done private X to change the same thing, achieve the same thing. First private, I can put on a work share or a parallel. And first private says, create a private copy for each variable in this list, but initialize them with the original value. All right, and we'll have an example soon, okay? Then I have a clause that's only available on a parallel loop construct called Lastprivate. And it allows me to say, whichever thread did the last iteration of this loop, take its copy of that variable and copy it out of the construct. Because that's important, because what happens to a private when you leave the construct? What do you think? Rules of C, folks, what do you think happens? It's gone, right? So if I have a private and I come, on a loop work-share construct, and I come to the end of that construct, it's gone. Sometimes, either for debugging or whatever my program's doing, I want to know what that value was in some cases. So Lastprivate is a way for me to way for me to get some of that back. And it says, for this variable, I would only use it on a loop, work-sharing construct, and it says, whichever thread did the last iteration, its copy of that private variable, it will write out into the original variable in an exterior scope. Okay? And this will make a lot more sense as I go through the examples. I'm just trying to give you the lay of the land, then we walk through the examples. I can override the default rules. In principle, and it gets complicated, and really only one of these is useful. Default private, default shared, or default none. All right? And they change the rules. The default, what it is with you doing nothing, is default shared. And this says, I hit the construct, I have a bunch of variables that exist prior to the construct. When I need to disambiguate, I'll call those the original variables. All right? I hit the construct and I'm going to do something. I'm going to create private copies. I'm going to do something. Okay? What default does is it changes the rules of what's the do something. Okay? The case you get for free is default shared. Those original variables that existed prior to the construct are shared inside the construct. That's default shared. Default private says those original variables prior to the construct, they're all going to be private. And I'm going to say more about private in a moment. And I'll get to your question in a moment. I'm not aggressively ignoring you. I'm just lightly ignoring you. No, we'll get there. All right. All right. Default none. Default none is your friend. Because default none says we require, and I will report as a compilation error anytime when you don't tell me what the sharing status of a variable is. All right? For debugging, that can be a real lifesaver. Now, subtle little point, I always have found this irritating, but that's the way it goes. Default private is available only in Fortran. Default private is not available to C. And do you want to know why? I was irritated by this because we try really, really hard that if you know OpenMP for C, you immediately can move into Fortran and move around languages. So anytime there's an asymmetry between the languages, it just pisses me off. But here's the thing. There are a collection of items inside the C standard libraries that look like variables, like standard in, standard out, that kind of thing, which are actually, in many cases, sometimes implemented as macros. And the compiler doesn't have a clue what to do if you tell it to create a private copy of a macro. So there is no way for the compiler in general to safely do a default private in OpenMP. So that is why typical compiler people are lazy. Aren't they? Do we have any compiler people out there? You're fundamentally lazy, right? You know, that's why they have their escape clause on data races. I don't want to figure out what to do if there's a data race. I know, we'll say the program's illegal. Then we don't have to worry about it. Hey, we're great, we're smart. You know, same thing here. It's like, I don't know, man, there's some boundary cases that are really tough on default private. I know, we'll just say you can't do it. You know? And then get away with it because they're God's gift to humanity. They're compiler people. Oh, I'm sorry, this is being recorded. Compiler people, I honor and respect you because I could do nothing without you. So thank you. All right. I've yacked at you so long. You know, you got to see examples. And the thing is, these clauses are nowhere near as complicated as I think I just made them sound. They're really, really easy. Look, and it's just some examples. By the time these examples are done, you'll see what I mean. All right, here's a piece of code, and there's stuff wrong with this code. But here we go. All right, first off, I just want to remind you. So look at the variable temp, TMP. Then I'm going to have a parallel region, and I'm going to create a private copy inside this parallel region of temp. So I have the private temp. Now, when I need to disambiguate what I'm talking about, the copy inside the construct or the copy that exists outside the construct, I will call the one outside the construct the original variable. And that kind of makes sense, because if you think about a compiler transforming this code, it has some original concept of what that's variable. So when I go private temp, it has to know what to do. What's the storage class? What's the type? You know, it has to have some idea of what it's going to do. Okay? So that int temp 0, that value of temp is the original variable. Then I have my construct private temp, and then I come into my program. But notice I go temp plus equals j. Can I do that? Well, I can do it, but what's wrong with that? And I say right on the slide, you know, when a private variable is created, it's not initialized. So go back and think about the way we used x in our pi program. You know, x equals I times step, or I plus 0.5 times step. So I'm always assigning it before I use it. That's where you would use private. You need to create some space where you're going to assign it before you use it, so you don't want to go to the trouble of initializing it. So private does not initialize. Now, when I get to the end, I'm going to print temp, and the value it's going to print is the original, which makes sense, because when I leave the scope of the construct, the variable goes out of scope, and by the rules of the C language, it goes bye-bye. All right, so we revert back to the original copy. Really easy. Let's look where it gets messy. Oh, man. I often skip this slide, but then I find out if I skip it, I just get asked questions. All right, look closely at this situation. I've never been stupid enough to write a piece of code like this, but you could. So I have a file scope variable int of temp, and then I have a function called danger, just to remind us all that please don't ever do this, right? Okay, then I had set temp to a value. Now I create a private copy of temp, and I call for on my parallel region. Then I call a function work, and work goes and has an extern to temp, where it sets temp equal to 5. Now we're going to try and print temp when that's over. Oh my God. What copy of temp, when this function does extern int temp, what copy is it going to grab? Is it going to grab the file scope, original variable, or is it going to grab the private that exists within the scope that the function was called? It's completely ambiguous. So this is specifically forbidden in OpenMP. If you are dumb enough to do this, you deserve whatever happens to you. All right. So, and someone asked earlier, and actually it was a very good question when they asked it, is there a way for you to check the original variable from inside the scope where you have a private variable with the same name? And the answer is no, and if you try to do it, I'm going to slap you. All right? Or, well, the compiler will slap you. We talked about Firstprivate, so here's an example with Firstprivate. And so I have some increment variable 0 that I'm going to use for incrementing my computation. I'm going to, you can see how I'm using it. So I have Firstprivate because I want it to have a well-defined value. So the way Firstprivate works is it does the same thing as private, but then it will assign the original variable's value to the private you just created. So this is what you use when you're doing something with a variable and you want it to have a well-defined value inside the region. And if you're using C++, they use the copy constructor. So yes, we were good enough to say which exact constructor. I think that's pretty clear. And Lastprivate, I think that's also pretty clear. So Lastprivate X, it creates a private variable just as before, but when you're all done, whichever thread did the last iteration of the loop, it's going to take whatever that thread's value of X is, and it's going to assign it to the original value upon exiting scope. All right? Now, clearly, I can't have something that's both private and both shared. So if I have a private clause with X and a shared clause with X, the compiler will tell you you're an idiot and don't do that. Right? In general, a variable can only appear in one data environment clause. There's one and only one exception. I can have a Lastprivate and a Firstprivate, or a Lastprivate and a private. So Lastprivate can mix with the other privates. And that kind of makes sense. You know, there are cases where I want the variable to have a well-initialized value coming in, and I care about its value coming out. So I want to do both. All right, here comes the test. I have variables A, B, and C. I've initialized them to 1. I have pragma OMP parallel private B, Firstprivate C. All right? I want you to ask yourself, are A, B, and C private to each thread or shared? Think about that. Then, what are their initial values inside this parallel loop, inside this parallel structure, this parallel region, sorry. And what are their values after the parallel region? Okay, I want you to think about that long enough so you have an answer for all those questions. Is A private to each thread? It's shared, isn't it? Good, you passed. Okay, what about B and C? Private, good, good. Okay, now I want you just to call them out all at once. When we get inside the parallel region, we first get inside. What's the value of A? 1, okay, that's good. What's the value of B? Undefined, good. What's the value of C? Oh, that's awesome. Now, we get to the end, and what are our values? What's the value of B after I leave the construct? 1? It's 1. It goes back to the original value. What's the value of C? C. It's 1. It goes back to the original value. Okay? And what's the value of A? It's whatever you got from inside the parallel region. Good. I'm going to say that all of you passed. Okay, good. Round of applause. You all, come on. Round of applause. Come on. Yeah. Let's get some enthusiasm. Jeesh. You're learning the greatest programming model in the history of humankind. So you should be, you know, Bill and Rusty aren't here to defend themselves against me. So, all right. So that's the basic clauses. And you know, I'm just gonna be really quick here. I don't care about default shared. I don't care about default private. Default private has been a lifesaver to Fortran programmers because they can't declare, at least until recently, but basically in Fortran you can't declare your variables inside the scope. So for Fortran programmers, they're running into this situation where they'd have line after line after line after line of pragma stating by hand everything that's private. So they tell me that Fortran programmers actually use default private quite a bit. But let me just tell you, the only one of the default clauses that really, really, really matters is default none. Because then you are forced. It's like, why is it a good thing you have to declare all your data types in C, and why does Python suck? You know, I don't know if any of you have tried to do a major Python program before. I hate it. It's just like, what an anti-productivity language, because the number of bugs you run into because of data declaration conflicts, what a mess. There are data declaration conflicts because all the data types are implied, and what a mess. It's so much cleaner if you have to declare everything. Okay, so that's what default none does, is it forces you to think about, oh, yes, this is shared, that's Firstprivate, so it forces you to go through and do all of that. All right, now we're coming to a juicy exercise. I've given you a program, and it computes the area of a Mandelbrot set. Compile it and run it. Oh no, when you do, you will find it gives you the wrong answer. There are bugs in this program because I was really lazy. Actually, Mark Bohl at EPCC wrote this. So Mark was really, really lazy and screwed up. So your job is to fix it. And I'm going to give you a hint. One of the problems is with the data environment. But let me warn you, there is more than one problem. All right? Now, if you're a hot shot who goes through and you very, very quickly solve this problem, you're not done because see if you can optimize it. There's many different ways to do this little piece of code. So I'm going to leave you alone. This is one that's a little bit messy, and you have to think about how to debug OpenMP and how to debug this program. So here's the program that you were given. And when I run this program, I get an incorrect answer. And not only is the answer incorrect, each time I run it, I get a slightly different incorrect answer. When you see that, what do you know is happening? What do we call that? It's a race condition. So the term race condition refers to a program, usually a parallel program. I'm going to say always a parallel program, where the answer you get from that parallel program changes as the operating system schedules resources differently. Okay? That's a race condition. Now, typically a race condition, not always. In fact, later on today, we'll do a race condition that doesn't happen because of this. But usually when you get race conditions, it's because you have a data race. And the data race is when you have reads and writes conflicting with each other, or literally the threads are racing to see who can get their write established first. So it's called a data race. All right, here's my program. Wow, let's see if I can figure out what's wrong with it. Well, what I would do is I would take this default shared and I would change it to default none. All right? And then I would go down and I would sit down and I would create the right sharing class of every single variable. And if I did that, what am I going to immediately find out? If I did that default none, what would I see? Well, gee, I will be made automatically private because it's the loop I'm splitting up. But J is not private. J will be shared. So I need to make J private. That's my first race. The other problem is EPS. All right, see, I'm going to take this value, compute it, and add this small little fudge factor to it. What value does EPS have? Call it out. The value of EPS. Undefined. Yeah, I guess just this isn't a really enthusiastic. Undefined, oh my God. Okay, we can get real excited here. Yeah, EPS is undefined. Okay, so I have to give it a well-defined value. All right? But there's a nastier bug. If you look inside test point, all right, test point. Well, I have this variable z, and zi, gosh, where am I getting the c from? It's a global. But if I declare it private, which one is it going to pick up? Remember, we talked about this. Which one is it going to pick up? Neither. It's undefined. It's undefined. That's bad. That's like really, really bad. So what I did, what I did is I changed test point So I passed in the value of C. So I made it completely clear which value of C I was working with. I'm not saying this is the only solution, but you have to make it unambiguous. So now test point is passing in as an argument C. All right? So I have C is private, J is private, I'm okay. First private EPS is how I got EPS the value. And then the last thing is num outside. That was another race. So I protected that with an atomic. Now there's another solution. I could have passed num inside into the argument list, and I could have done a reduction on it. It's not like there's only one way to do this. The reduction approach would be really, really handy if I thought there'd be a lot of contention on this atomic. All right? But I kind of said, you're going to go through this while loop, and you're going to keep going until you get divergence as measured by the magnitude of your complex number being greater than 4, the magnitude squared. Right? And so I'm going to assume that all the threads are not going to be likely to hit that at the same time. So I felt comfortable putting an atomic here and just sort of assuming that it's uncontended. That's what we use when we talk about locks or mutual exclusion constructs. If the threads are likely to hit it and no one else is holding it, it's very low overhead. So uncontended locks in a well-designed system should be low overhead. So I'm confident that this performance of putting an atomic inside that loop is probably going to be okay. It's definitely the first thing I would try. But you could do that with a reduction. All right? Are there any questions about this example? Yes?
I'm confused. Why did you not have to make I private, but you did have to make J private? What am I missing there?
Right. Okay. The question was, why did I have to make J private, but I didn't have to make I private? Let me tell you, I have a very small brain. It's because I paddle kayaks a lot, and all that cold water shrinks the brain. So I usually just make it private. It doesn't hurt. If you look at the code I write, I tend to over-specify the storage class. However, OpenMP for the loop that is being parallelized will make the loop index private for you. And OpenMP does that because there's absolutely no reason we can think of that you would want it to be anything else but private. But we can't make assumptions like that for the other loops. I'm trying to see if there's anything I skipped. I do have to say that to me, the key in debugging this, as I said, is the first thing I did is I went through and I got rid of that default shared and called it default none, so that it forced me to explicitly declare the status of everything. To me, that's the key of debugging these sorts of problems. The other key, and we're not going to talk about it at all, because it's not portable and I focus just what's the specification say. But if you're working on a machine on a regular basis, learn how to use the parallel debugger, learn how to use the profiler. The thing is, it varies from machine to machine, so I don't even find it useful to talk about. But obviously, the super programmers who are extremely productive, one of the features that distinguishes them from the mere mortals like me is they make heavy use of tools. So even though we didn't in this example, using good tool chains can really help, especially when we talk about optimization. So let me be clear. At this point, the traditional loop-based, SPMD-based, old-fashioned OpenMP that your parents learned when they were in school, you now know. I've now covered it. You know how to create threads. You know about the major work share constructs. You know the major synchronization. Yeah, there's some details about the memory model. We haven't talked about flush in detail. There's a few other little things. We've talked about the data environment. But when people talk about using OpenMP, and when people talk about OpenMP in an existing application, you've now pretty much covered the bulk of it. And you're to the point now where you could download the spec and read the parts we've covered to fill in some of the boundary cases I've skipped because I'm trying to get this through in a day. So you've got the core. Using the SPMD pattern, you can do almost anything. It's very, very general. MPI programmers love it and know it well, and have proven that if you're willing to work at it, almost any algorithm you care to work with can be handled through the SPMD pattern. And remember, let me be very clear. That's where the threads say, what's my ID? How many threads are there? And then I do everything else just by looking at ID. Oh, if I'm ID so-and-so, I own these pieces of the data structure, and you just do everything. So it's very, very general, very, very error-prone, very, very brittle, but it just works, all right? Then we talked about what is traditionally the most common way people use OpenMP, which is find your loops. You write your MPI program, you get your MPI program working really, 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 really well. Then you go onto each node, and you find the loops running on each node, and you parallelize those with OpenMP. You now have a hybrid MPI OpenMP program, and you've made the world safe for democracy, and everything's really wonderful, and it's just great, okay? The problem is that there are applications that just don't fit the loop-based approach. Not everything in the world maps onto loops. And there are applications that are highly irregular or require some other, like a recursive decomposition or some other breakdown that you just can't cleanly turn them into loops. But you don't want to build everything from the ground up with the SPMD approach. Because that's what SPMD does. It says, you got the ID, you know how many threads there are, you can do whatever you want. And you're right, you can build schedulers, you can build tasking systems, you can build irregular decomposition, you can do all sorts of crazy stuff. But you're doing it yourself, and it can get messy. And most of you don't know how to do it right because you shouldn't. You're physicists or engineers, not computer scientists. And computer scientists, as much as I like to pick on them, they do have some value. So, long, long ago, we added tasks to OpenMP. And the idea was to provide a high-level construct that greatly expands the universe of algorithms that you can handle just through high-level directives. So this is to expand the functionality of OpenMP. They've been around. At this point, my fuzzy little brain doesn't remember exactly when they came into being. It was OpenMP 3.0, whatever year that was. They first started working on them around 2000, so very early in the lifespan of OpenMP. I think it was 2005-ish or so before they officially made it in, maybe 2003. They've been around a long time, but people don't use them as much as I'd like. But I think as HPC applications become more broad and diverse, and as hardware platforms become more diverse, tasks are really coming into their own. And I think it's important for OpenMP programmers to understand them. So let's go into tasks. A task is just an independent unit of work. Okay? That's what we mean when we say a task. Now, the task has some code to execute and an associated data environment. Now, the reason it took so long to get tasks into OpenMP, it was a period of over 3 years of very hard work before we got tasks into OpenMP, is we had to understand how the data environment of tasks interacted with the larger data environment of OpenMP. And I won't go into it, but those of you who want to become real hardcore experts of OpenMP, download the spec and read it. And what you will find is we had to go back to the very core definition of OpenMP and tweak everything so that everything is in terms of tasks. Implicit tasks, implicit threads, implicit task environments, it's just, all this, and it had to get done so that we could unambiguously talk about how tasks interact with the rest of OpenMP. Okay? So it's, as I said, some of you will be interested enough to go and dig into all that and go there. Most of you won't care, and that's perfectly fine. Just trust me. we have defined how the tasks work together with the threads, work together with all the other data environments, so that they are not a grafted-on extra hanging off the side of this multi-threaded OpenMP. No, they're tightly integrated together into a larger whole. You basically create a collection of tasks, and then the threads in the team will go through and do the work of the tasks. So you basically have whatever thread encounters the task construct, it has the choice of saying, I will work on this right now, or it can say, I will defer this work until later. So what you can end up with is this picture, where I'd have a serial job consisting of these 3 tasks. I use a different color for each one. And I can pack them into a queue of irregular size, and then my threads will go through and execute them. And I think you can see, even in this simple picture, the kind of the value of what we're talking about here. Because obviously, for 3 tasks, it's not a big deal. But imagine it was 3,000 tasks, and I have 10 threads. This gives me a level of dynamic load balancing. And because they're tasks, they're not tied to a loop construct. So I have a much more flexible concept of load balancing than I can get necessarily from a loop. So you basically, a task has a structured block of code. And so inside of a parallel region, so remember, a parallel region is what you get when you have a parallel construct, open bracket, close bracket. So if I'm inside a parallel region and I hit the task construct, the thread that hits that task construct will package up the code, take that code block inside the task construct, take the data environment associated with that task construct, and drop it into a queue, or execute it immediately. And a task can create other tasks. So if you think about recursive algorithms, this is very much created with those in mind. So you have a task that splits a problem, and each task that it splits the problem into will be a separate task, which, by the way, will split the task again, which will split the task again. So you can have these recursive structures of tasks and handle whole classes of problems that were very difficult to handle with OpenMP before. So let's give a simple example. So the task construct is pragma OMP task, and then a collection of clauses. And then you have a structured block. So looks very familiar at this point, I'd imagine. Okay, as always, nothing happens unless you have a set of threads. So pragma OMP parallel creates a team of threads. Then I'm going to have pragma OMP master. So what I'm doing here is I want one thread to create the tasks. That's what I'm using the pragma OMP master construct for. Or pragma OMP single. I'm going to have one thread create the tasks. All right? So now one thread goes through and it creates a task called Fred, and a task called Daisy, and a task called Billy. And it's going to put those tasks onto a queue. Now, after the master construct, everyone else just passes immediately to the end, where they then hit the barrier at the end of the parallel region. So everyone hangs out at that barrier and either does nothing, but now all of a sudden tasks show up in the queue. Those threads waiting at the barrier will start working through those tasks. All right, so this is the basic model of how we compute with these tasks.
These tasks are independent?
Are the tasks independent? Well, if the program is to be correct, those tasks had better be independent. We will later talk about how to deal with dependencies. But let me be really clear. We're still talking OpenMP. You know, I haven't stepped outside of OpenMP. So let's say I had shared variables. Those tasks can be operating on shared variables. So I can have any kind of dependency we've ever talked about before is still at play here. So in the classic model where I'm just going to dump them on a queue, yeah, independent's the easiest. But there can be dependencies. So I still need to think about race conditions and shared data. All that's still present. Okay? So I create some threads to parallel construct. The first thread's going to package the tasks up. Tasks are going to be put onto a queue. They'll be executed by some thread. I don't know the order. Someone's going to execute them. And let me be really, really clear. An implementation has the right for that thread that creates them to go, you know what, I'm just going to execute this. I'm not even, there's not enough work to bother putting it on the queue. So a conforming implementation, I don't know of any that would be dumb enough to do this, but a conforming implementation could have the master thread execute Fred, execute Daisy, execute Billy. But I guess I could see if a compiler inlined those and those were just a few instructions each, it might even make sense, which is why we have it in there. All right, are there any questions about the task construct? Yes?
What's the difference between this and OMP sections?
Oh, wonderful question. Wonderful question. What is the difference between this and the sections construct? Okay? On the surface, not much. The difference comes as you dig into the low-level details. Okay? The sections are, first off, you can't nest sections, you can nest tasks. What's happening here, though, is this is very much a style of programming where you have work queues and you're populating arbitrarily dynamically sized work queues. Sections typically, as I said, are implemented in terms of statically scheduled blocks of sections. So this is a much more scalable scheme where you're assuming there's a work queue of deferred tasks. But in this case, with just 3 tasks, this looks exactly like the sections clause. So your question makes wonderful sense with these kind of PowerPoint simplified examples. Okay. All right. So we have an exercise. Inside the, I think I gave you this in the exercises folder. If I didn't, you can write it yourself. I want a program that's going to have a race condition. Okay? It's going to print, I think race cars are fun, or it's going to print, I think car races are fun. Okay? And I want a race condition. Each time you run it, I want it to potentially print either one of those 2 statements. All right? Basically, I want you to use tasks to print the indeterminate part of the output. So the race and the car, right? So you're going to print the part, I think, with a print statement, and then you're going to print the race and the car parts in a task, and then well, you get the idea. Then I'll print the S and the R fun in a separate statement. So that when you run this tasking program, I should get, sometimes I think cars are fun, car races are fun, and sometimes I think race cars are fun. All right? This is just to make sure you know how to spell task. Go for it. This should be really, really quick. Really quick, just like bam. Okay, is anyone done yet? Okay, maybe it's not quite that quick. All right, let's go. How many people got it to work? Oh, a good subset, but not everyone. That's okay. So here's my solution. As I said, I was hoping this would be really quick. If it wasn't, it's my fault because I didn't explain something clearly enough. So here it is. This is going to print, I think car races are fun, or I think race cars are fun. All right? And because I don't control the order that a task executes, it should be a race condition. I should get different answers depending on how the system schedules those tasks. Now, so there I go. I have print, I think. Now I'm going to create a parallel region with some number of threads, and then one thread. And I pick single because I have a long-term love affair with single. I think single is a marvelous construct. And if you want to know what I mean, imagine what happens if you do single with a no wait. But at any rate, I have single, and then I have a task that prints car and a task that prints race. Then, following the close of the parallel region, I print S, R fun. So as you can see, it'll be race cars or car races are fun. All right? And the goal here was just to give you the concept to play with of what it means to have one thread encountering the tasks and populating the queue, and then the other threads hanging out in the queue, executing tasks as they get to them. Are there any questions about this example? Some of you who didn't quite get it done, is there a specific point that hung you up that you'd need help with? Yes, in the back.
So,
It will change.
can I put a low weight on the single over here? Would it be a good idea? I mean, not in this case, but maybe in general.
Could I put a no wait on the single? You know, that is a marvelous question. And I'm not sure I know the answer. And here's why. The definition, and we'll have a couple slides on this later. My understanding of the definition of how tasks operate is this barrier here. No one will go beyond this barrier until the tasks within the construct that encountered it complete. So I'm not sure it would honor the no wait. But I have to tell you, I do not know for sure. Okay? But the definition, when we get to when do tasks complete, you'll see that we say the tasks complete at the end of the barrier of the construct that encountered the tasks. So we'll see. That's a great question, though, and I'm not absolutely sure I know the answer. Yes?
It's going there per job to a queue. You mean it's actually a queue, or it's just a bag of jobs that you can grab?
All right. The question was, I used the word queue, and many of us talking about tasks use the word queue, but is it really required to be a queue or a bag? Okay. We speak sloppily. It does not have to be a queue. Okay? It can be any kind of structure, and in fact, what I call this pattern is work pile. I think Arch Robinson uses that term as well when he talks about these. Just to be absolutely clear that we're not specifying what data structure is used to manage these. It does not have to be a queue. So let's dig into tasks in more detail. So when do the tasks complete? And where are the points in the code we construct where we know they will complete? All right? Well, they complete at thread barriers. So the tasks generated in the current parallel region will not proceed past that region until all the tasks complete. Now, there's a directive I'll give you an example of in a moment called task wait. And it defines an intermediate point where basically it will not continue until the tasks defined in that scope have completed. I'll give you an example of what I mean of that in a moment. All right? But basically, it applies to the tasks generated in the current task, not to any tasks created inside those tasks. We'll get there. Let's look at this example, Pragma OMP parallel, Pragma OMP master. So one thread's going to create the tasks, creates Fred and Daisy. The Pragma task wait says that it will not continue past that point until the tasks created within the task scope complete. So task Billy will not be put onto the work pile until task Fred and task Daisy complete. So this is a way for me to create an order precedent between tasks. Okay, so that's what task wait means. Now, but task wait only applies to task Fred and task Daisy. If task Fred and task Daisy went on and created a whole bunch of tasks themselves, it does not have to wait for those. That's what it means when I say that task wait doesn't wait for the descendants to fail, to complete. Task wait just says, look, I'm waiting on Fred and Daisy. I'm not waiting on their kids. You know, Fred and Daisy pop off lots of children. That's their business. I only care about Fred and Daisy. All right? But the barrier at the end, I care about Fred and Daisy's kids too. So the barrier at the end waits for everything to finish before it goes on. All right? So it's not as complicated as it might sound. Okay, let's get another example just to drive this home. And this is kind of the motivating example of why we created tasks. So let's go through and think about this. So I need to create the threads. Remember, without a Pragma OMP parallel, there's never any threads. Okay, I'm going to have one thread build up the set of tasks. So Pragma OMP master. So now I'm going to pick up the task head. That's the P equals list head. Now I'm going to walk the list while P is not null. I'm going to go through and I'm going to create Pragma OMP task Firstprivate P. I'm going to explain that Firstprivate in a moment. Okay? Firstprivate P will process the task P. Then I'll create the next task, P equals next P. Then I'll come around. If I'm not at the end of the list, I'll create another task. So I'm going to create a big queue of tasks that's filled with process P. We couldn't do this with section because notice sections, I have to statically know how many of them there are. Here I don't know how many there are. So this is vastly more general than sections, okay? So only one thread packages the tasks, okay? I make a copy of P when the task is packaged. Now think about it. I have a list. I have a list pointer to something. I don't care, but it's a body of work that I'm going to be able to work off of when I process that item on the list. I need to capture its value at the time the task is created. And they kept, when we were sitting around at the meetings defining OpenMP, people were like, well, we should add a capture clause or some other clause. And I was like, wait a minute. It's exactly the same as Firstprivate. Don't create new terms when we don't need them. All right? So exactly what is it doing? Well, you know this already. I'm going to create a private copy of P for each task. You know that concept, right? Oh, but I need to initialize it with the original variable so that that is held with and captured and stays with the task. It's just Firstprivate. No new concept here. So Firstprivate P means that when I put process P onto whatever sort of data structure is going to manage it, I apologize, I'm going to keep calling it a queue because I'm sloppy, but the spec does not state it has to be a queue. Okay? I'm going to put it on the queue to be processed, but I want to capture that value of P. All right, so that goes on the stack. Then the thread that's walking through collecting the tasks will grab the next value of P, and then off we go. Now the way this executes, just to belabor the obvious and drive this point home, because I want to make sure you really deeply understand this, is imagine I have the master thread, thread 0, and here you see what that thread does, right? While P, it's going to package up the task, and then it's going to go on to the next P, and it's going to continue through that while list until it's done. Then when it's done, it's going to go through and it's going to look at all the tasks on some other structure, whatever structure tells it what to do. It's going to go through and work on those and execute them until they're done. Then it'll enter the barrier once it's done. Now all the other threads, they're going to hit the barrier, right? Because that's what happens with master. What are they going to do while they're sitting at that barrier? They're going to notice, hey, there's tasks here to do. So now they're going to, while there are tasks to do, execute the tasks. So from an execution point of view, with that code I just showed you, this is what's going to happen. I want to emphasize, we got the master threads going through, capturing the state of the task, populating it into a data structure. When it's done, it joins the team to execute those tasks. Meanwhile, everyone else the whole time has just been going through and executing the tasks. So this gives me a very dynamic way to dump work onto some kind of structure for my collection of threads to cooperatively work through. It's an incredibly flexible and very, very powerful way to represent work that I want to happen in parallel. Okay, questions? There was some back there. Yes?
Is it possible to have multiple threads create tasks because the other thread that is sitting there?
Is it possible to have multiple threads creating tasks? Yes, absolutely. There is nothing that says it has to be just one thread creating tasks. The data structures that hold the tasks are thread safe, and they're perfectly happy having multiple threads dumping in. I even have an example of that coming up. So there is nothing in the task construct that says only one thread can populate the tasks. Turns out the most common way tasking's used is with this pattern. This is kind of the standard way we do it, but nothing says that you can't have multiple threads creating tasks. And I can't stress enough, inside a task, I can create tasks. So tasks can be nested. Tasks can create tasks. In fact, as you'll see with the example I'm going to turn you loose on in a little while, your next exercise, you will need to do that. So yes, this indeed happens. Question all the way in the back. Yes?
How much does it cost to package up the tasks?
I haven't measured it, so I do not know. But if you think about it, you know, it does have some overhead. You know, we got to take a code section, a pointer to the code section. We got to capture the state of the data environment, okay? In addition to that thread, that's any internal control variables that are required. So there's a significant block of memory associated with that state. So my hunch is that it's not cheap. In fact, one of the things I'm going to say, like at the end closing slide of the tasks, is only use tasks if the other constructs in OpenMP don't get your job done. You know, after you fall in love with tasks, don't go, oh, I don't need parallel loops anymore. I can do it all with tasks. I think tasks probably have quite a bit more overhead. You know, you really want to use tasks when you have dynamically varying blocks of work with irregular structure. You know, that's when you just, nothing else but tasks are convenient to use. Yes?
So if you have a task, then you have its children tasks, then you have to back up the status of the system.
Yes. Let's just be clear about the costs. Creating a task represents some overhead. I don't care if it's one thread creating the tasks or if it's nested task creation. The process of creating a task is I have to capture, let's just step back a second. The definition of a task is a block of executable code and its data environment. Its data environment, you know, if the data environment's big, if there's, you know, big private arrays, and we're talking inside a task, you can put any kind of OpenMP code. So the data environment could be big. There could be substantial overhead here. Okay, this is not a cheap task. Yeah. Yes?
So there is no guarantee which task is assigned to which thread.
There is no guarantee, you are correct, there is no guarantee of which task gets assigned to which thread.
So in case of a parallel for loop where I'm actually creating implicit tasks, I presume, so does that guarantee also not hold in that case?
A parallel for loop does not create implicit tasks. A parallel for loop creates, you know, it assigns iterations to threads. So there's a fundamental difference. That's right. In fact, it gets subtle, and I'm not really going to go into it, but we even added a separate construct for loops that you do want to create tasks. But do not think that the task is the same as a block that's assigned to a thread from a loop. So this comes back to the question that someone asked earlier, can I have multiple threads creating tasks? Here's an example, all right? Pragma OMP parallel, I got to create my threads. Pragma OMP 4, okay, great, I have a for loop. And I'm going to create a private copy of P, so now each thread has a pointer to the linked lists. All right, now I'm going to go over my loop, int I equals 0 over the number of lists. And now I'm going to point to the head of a list because I have an array of lists. And I'm going to point to the head of the list, and each one of my threads is going to go through while P, Pragma OMP task Firstprivate. That looks like exactly what we had before. But you see, this is an instance where I'm going to have many threads go through, and all of those threads are going to be populating tasks into some kind of data structure. Okay? So all threads package the tasks. A couple more things I want to talk about before I turn you loose on the next exercise with tasks. The data environment clauses you already know, shared, private, Firstprivate. You can use those with tasks. You will need to use those with tasks. You've already been exposed to Firstprivate. They're kind of like what you're used to, but things are a little bit different. And they're different in that they capture the state of the variables in question at the time the task is encountered. A private is going to create a construct on initialized storage, and it creates created when the task is executed. Shared, you get the construct to the storage with the name pointed to when the task was encountered. All right? And Firstprivate we've already described. So if you look at this example here, I'm hoping this makes sense about the default. I have pragma OMP parallel. I have a shared array, a shared object A, a private object B. So now I have a task, pragma OMP task, int C, and it's going to call a function. So I hope you can all see that A is shared, B is first private, and C is private. And I slipped something in on you that I think the text describes, but let me explain. When you encounter a task, if the original variable is private, it is implicitly made first private. And this is part of a general rule we have in OpenMP. If we think a use case is just the way you're almost always going to want it to make the code work, we try and default to that case. So if you call a task and a variable is private when you call the task, we think it's probably likely you want that first private inside the task. So in this example, B is first private inside the task, C is private because you declared it inside the task, and A is shared. All right, but I think this is too much detail. I want to give you another example and then give you an exercise to work on. All right? Let's look at Fibonacci. This is one of the stupid examples we use all the time when we talk about recursive algorithms. And it's stupid because if any of you ever computed a Fibonacci sequence this way when you really cared about having it, you should be fired on the spot. Okay? No one is implying this is how you should compute a Fibonacci sequence. But what the heck, right? So I have my function for the Fibonacci sequence. If n is less than 2, I just return n. This is the standard recursive algorithm. All right? Then I'm going to go, if I get the Fibonacci number, I'm going to go x equals fib minus n minus 1, y equals fib n minus 2. Then I sum the two of those together. And so I'm going to recursively go through, and I will eventually end up with a proper Fibonacci number. So that I can call that with 5,000, and I'll get the 5,000th Fibonacci number. I hope this looks familiar, sort of a kindergarten recursive function. I mean, hasn't everyone seen this before? This is like standard functional programming 101, right? So look how this would be in parallel. So, okay, I have my Fibonacci sequence function. I'm going to call it recursively. So if n minus 2, return n. So I have my base case is what we call that with a recursive algorithm. My base case is defined up front, that if n is less than 2, I just return n. So it's going to be n equals 1 or n equals 2. All right? Great. Now I'm going to create a task to do Fibonacci of n minus 1. I'm going to create a task to do Fibonacci of n minus 2. And then I'm going to do a task wait, because what I want to return is the sum of x plus y. Are you with me there? Okay? But I don't want x and y to go out of scope because I want at the end of their task, because I want them available for that sum. All right? No problem. So I have pragma OMP task shared x, so that I know that the x will exist after the scope. Pragma OMP task shared y. Just to define, I really, really, really want x and y to be visible after the scope of those tasks. So off I go. Any questions about this? Because the exercise I'm going to give you looks very similar to this. In fact, what you're looking at here is a basic pattern associated with cache-oblivious algorithms. So anytime someone talks to you about I wrote a parallel cache-oblivious algorithm, this is the kind of pattern they're using. They're recursively walking through whatever their data structures are, all right? And they're splitting off tasks to do a block, and they're sort of creating this tree of tasks down to the base case. Then as the base case resolves, they unwind the tree and jump back into the right answer. We'll have more to say about that in a moment if we get the time. So this is a very, very common pattern in classes of important algorithms. Question?
Does the function fib know that it's being called inside a parallel region?
Nope.
No, so you just put these task pragmas in there, and you don't care whether it's called in a parallel.
Oh, wait a minute. You know, I'm sorry. I have to come back. I have to back off of that. You know, this is going through an OpenMP compiler. The OpenMP compiler knows that there are task constructs in here. All right? So it knows that it's prepared to be called within an OpenMP context. All right? But let's be really clear. Pragma OMP parallel, then I call fib. But I could have called fib outside of the Pragma OMP parallel. I didn't have to call it inside a parallel region. What would happen if I didn't call it in a parallel region? Would I get any parallelism? No, there'd be one thread. So the constructs OMP task shared X, OMP task shared Y, OMP task wait, if you call them outside a parallel region, they become no-ops. It's still a working program, okay? There's a term you will see in the OpenMP spec, and we're getting pretty subtle, but I'm just going to call the term, define the term for you. Pragma OMP task shared, what you're seeing in fib, if they're called outside a parallel region, we call those orphaned constructs, okay? Because they don't have a team of threads to bind to. So there's nothing that says I must call this function inside a parallel region. However, you have compiled it with an OpenMP program, so it's going to put in the hooks it needs to turn that into code that it can execute with tasks. And it's interesting thinking about what it's going to have to do, but I guess we shouldn't go there. You know, that's like another course in OpenMP, which is compiler transformations for OpenMP. Yes?
Is it possible, I mean, if I call fib outside the parallel region, is it still possible to get an interleaving of...
Nope. If you call this outside, okay, the question was, would I get interleaving of tasks if I called this outside a parallel region? And the answer is nope. If you call it outside a parallel region, it's a serial program. Since it's a serial program, there's nothing to interleave because it's running on one thread. If I call this inside a parallel region, now I'm populating data structures to hold tasks, and threads are going to execute those tasks as they fill up these data structures, and then I can get interleaving and parallel execution.
But it's always possible for the single thread to suspend execution, take up the task, and then resume the...
Okay. For the sake of time, I'm not going to have time to go through this in a great amount of detail. But let me touch on this concept briefly here. If you create vast number of tasks, the data structures you have for managing the tasks can overflow. This is one of the problems if you study creating task systems. This is one of the problems. You have finite space for holding tasks. You know, even if a task is half a megabyte, you know, you create 1,000 of those, you're in trouble. So the way tasking is defined, the threads creating the task can suspend task creation and switch over to computing the tasks. Wait until those structures are drained, then go back to computing more tasks. And if you read very carefully the way the tasking constructs are defined, we define thread switching and thread synchronization, task switching and task synchronization points that define the points where threads can drop task creation and go back and actually compute on the tasks. So this is very carefully built in to the definition of how these task systems are created. So the point is very important on any task system. If you just start creating tasks, if you give no mechanism for task creation to suspend while everyone works together to use up some of those tasks, if you don't do that, I guarantee you're just going to break systems left and right. And so this is built in. You know, the tasks can go, wait a minute, you've created enough tasks, let's go back and work with it. You know, the data attributes, I don't know, I hate putting this line in here. They can be tricky, but really not. You know, you need to think about it. If things are going to go out of scope, make them shared. If you want to capture the state, make them first private. Play around with it. It's a little bit tricky because it's just a little different. I should say that. They're a little bit different than what you're used to in the rest of OpenMP, but it's not that hard. I can't stress this enough. If the other parts of OpenMP, like parallel loops, can do the job, then don't do it with tasks. You know, tasks are all about irregular, dynamically varying, changing workloads, like traversing linked lists, like recursive algorithms. You know, if you can statically figure out how to break this into blocks that you're going to assign to threads, use a loop, for goodness sake. This is a line my friends on the implementation side put in. Don't expect miracles. There's a lot of overhead to these tasks. All right? So you want to be careful about how many tasks you create. And remember, there's a fair amount of overhead, so try and have a fair amount of work in each task. That's another thing that's wrong with that Fibonacci example. You know, are you going to get good performance out of that Fibonacci example? No way. Right? You want enough work going on in a task so that the overhead of creating it is not too bad. All right, I have a fairly simple, he says, example for you to play with. In the exercises directory, I have a recursive pi program. This is an important one to understand, because when people talk to you about cache-oblivious algorithms, this is the sort of thing they're talking about, these recursive algorithms. And we can argue whether they're good or not, but it's a worthy argument to have. And as a well-rounded parallel programmer, you should understand them. And so the idea is sort of a divide and conquer approach where you recursively split a problem smaller and smaller until it gets to a size where you can solve it directly. It's the same pattern as the Fibonacci example, but we're going to use it for my favorite little problem, a numerical integration to estimate pi. So saving you from having to write the starting point in this, I have in the exercises, I think I call it pi_recur. I believe that's what it's called. What I want you to do is take that program and using tasks, create a parallel version of it. And I'm hoping it'll take you 10, maybe 15 minutes. Several excellent questions came up. And it's like, it's hard to know where to begin. But hopefully my links work. Yes! All right. I'm all about patterns. If you take a semester-long course in parallel programming with me, we go through the core patterns, and by the time you get done with the course, you can look at most any parallel algorithm and go, oh, well, that's just an implementation of the work pile pattern. Oh, that's easy. So, you get the idea is to create an overwhelming sense of order to the confusing universe of parallel algorithms. And I think it's a valuable way to learn parallel programming. I think it's the right way to learn parallel programming, and almost nobody but me teaches it that way. At any rate, this pi example I gave you is the classic instance of the divide and conquer pattern. Charles Leislerson and his buddies at MIT love this pattern because this is the core of cache-oblivious algorithms. Now, if you've never heard of cache-oblivious algorithms, first off, I'm not sure I really believe in them. But, if you're going to call yourself a parallel programmer, you should build up over time an understanding of the major thrusts in research about different ways to effectively exploit a parallel machine. And there's absolutely no doubt that one of the major research thrusts in parallel algorithms are these cache-oblivious algorithms. So if you think about it, when we write, this particularly comes up with stencil codes and dense linear algebra, where you can block your problems into sizes a priori that map onto different features of the memory hierarchy. Okay, so I can cache block my algorithms. Turns out it's really important to block around the translation look-aside buffer as well. I have some wonderful examples with transpose where I can just sort of blow the whole thing to bits just by trashing my TLB. So, you understand the memory hierarchy, and then you block all of your loops so that they map onto the memory hierarchy. And this is what people do when they build something like the math kernel library or any of the optimized BLAs. This is the BLAS, basic linear algebra subroutines, okay? Any of those, the way they're implemented in hardcore environments is they're cache blocked and you find the right blocking for a particular architecture. Of course, the problem is you pick that up and you move to another architecture and you gotta start over. You have to block it differently. So it's a very, very sensitive, brittle part of how we work with our computing environment. So what the cache oblivious people say is that what you instead want to do is define your algorithm recursively and you pick just the base case. Remember where I said, like with the Fibonacci, right? You keep on recursing until you get to a small enough size that you compute it directly. Okay, what cache oblivious algorithms say is you keep recursing and splitting smaller and smaller and smaller and smaller, and then you define a base case that fits into your L1 cache, or whatever the appropriate level cache is. But now you just have one parameter. You don't have all these parameters for every level of the memory hierarchy, so you can write algorithms that are oblivious to the details of the memory hierarchy. And that's driven by these divide and conquer algorithms. All right, and it's easiest to see with a picture, where you start at the top, and you split into subproblem, you split into smaller subproblems until they're small enough, and then you solve, and then you recombine to turn all your sub-solutions into the final solution. And so that is what we did with this Pi program. And so you can see that we have the Pragma OMP parallel because I want to create a team of threads. I have my Pragma OMP single, which is going to call my PyComp, which is that recursive function. Then I have my base case when nFinish minus nStart is below my smallest size. At that point, I have to compute the block directly. All right? And then I'm going to call that recursively inside with shared on sum1 and sum2 so that I can sum them together. Here's the subtle point. That function is called within, that first function, PyComp, is called within a thread. So when I assign sum1 and sum2 and I declare them, they're declared within the stack of a thread, which means they are private. So therefore, when I go into the task for each of those tasks, the encountering thread has sum1 and sum2 as private variables. All right? It's going to capture their value. Remember, on int entry, they're going to act as first private if you say nothing else. That means they go away as you come out of the scope of the task. That's why I had to declare them as shared. Now, one question that came up repeatedly that was very interesting is what if I put on that loop for the base case Pragma OMP4? Okay? Wonderful question. I'm going to do something that one should never do in a tutorial or a lecture, particularly when it's videotaped. My understanding is that is illegal because OMP4 is a work share construct. A work share construct needs to be called by all the teams in all the threads in the team. So what you're doing by putting a work share construct inside a task is only one thread in the team is calling it. So I'm not even sure what an OpenMP runtime would be able to do with that. And I suspect, and after this lecture I will go through and look it up and see chapter and verse, I suspect that is not allowed. Now, but what if I did Pragma OMP parallel for my base case loop? That would be allowed, because now I'm creating a new team to encounter that work share construct. Now, what's going to happen if I do that, though? Each task is going to create a team of threads? Yeah. It could lead to a dramatic oversubscription problem. You know, I will get a huge number of threads as they hit that base case. So I'm not sure that's a good idea. But do you see that distinction of a Pragma OMP parallel for at least is well defined in an OpenMP sense, whereas a Pragma OMP 4 means I'm embedding a work share construct inside a task, which means only one thread is seeing it, and that's just going to break things. So hopefully I won't regret that. But at any rate, my results when I ran this, comparing them all, is I got very nice performance with my tasks. So I'm comparing the SPMD we talked about earlier, the critical section to remove the false sharing, my Pi loop, and I actually, on my system, got very nice behavior out of the Pi with tasks. And this was on my Apple laptop with a dual core. But one thing you will find is because tasks are not as heavily used as the good old-fashioned loop constructs, I personally have found much more variability in the performance of task-oriented systems. I remember situations just a few years ago where if the Intel compiler, it would speed up beautifully like this result, and the GNU compiler, the performance would suck. So I find a lot of variability in the quality of implementation of tasks. I think that'll change over time. Tasks are a part of OpenMP that is continuing to evolve. I can create dependent task chains. I have to pay attention to when tasks switch, so that I go from creating more tasks to computing tasks. There are several subtleties. So what I've given you here today is a nice introduction to tasks, but I haven't covered everything there is for you to learn about tasks. Little advertisement, at SC16, we have a tutorial called Programming Irregular Applications with OpenMP. That is an entire half-day tutorial on nothing but tasks. All right, but it will take a half day to go through all of them. So we're going to stop.